usual writing
Okay.
direction, but
No, that's all right. That's
okay,
good.
I can try.
Okay, so our next speaker is Viktoriya Ozornova from the Max Planck Institute for Mathematics in Bonn, who's going to talk about equivalences in higher categories. Again, you have 30 minutes for a talk, and then we'll have question time. Please go ahead.
Thank you. Thank you for the invitation to speak here. It's a great pleasure. And sorry for making all of you speaking English. So all of what I'm going to say is joined with Martina Rovelli, all of which is new. And so I'm actually want to discuss a theorem which is also joined with Amar Hadzihasanovich. And Félix Loubaton, and it just appeared on the archive. So let me get it out of my way, stating the theorem first, and then we'll go in reverse order in order to understand the words in the theorem. And I will state it at the moment quite roughly because it kind of does not make sense the way as I'm stating it. There is. And I will add adjectives to it as we go. There is a fully coherent omega equivalence. So a non-mathematical statement first is there is an explicit one. So you don't have a real notion of explicitness, so it's a somewhat vague. But I want to stay here, and I owe you still an explanation of what omega equivalence is and what fully coherent means for me. And I can add on some adjectives which are which are more mathematical later on. But let me start with this at first. And quite differently than Sebastian, when I say high categories, I don't mean infinity one categories at all. So my higher categories so far, I can also comment on the relation to higher weak categories or higher infinity categories. This also makes sense, but this is not the main body of my talk. So I don't mean this, and instead I mean really strict. So what I mean inside there is that this is not a full definition yet. But what I mean is we have some kind of higher morphisms. So one morphisms, two morphisms, three morphisms, but all of the compositions are defined and supposed to be strict. So those can be composed strictly. And there are still identities, there's still associativity the way you are used to it. Can be composed strictly, and they satisfy strict. So I can comment later on weak versions of this theorem, but for the moment I'm completely strict, satisfying strictly. So this is very different from what Sebastian was talking about, because you have all the way higher morphisms, all the way up to infinity, which we usually call omega because we want a distinction there. But those, as opposed as in Sebastian's setting, none of them are required to be invertible, and instead all of the axioms are holding strictly and not only weakly, satisfying strictly associativity, unitality, some interchange laws, and so on. Unitality. There are more. I'm not going into this. So this is my notion of higher categories for today. But before we go even there, let's ponder upon the notion of equivalence in a category. So this is somewhat classical, and all of you have seen this, I'm sure. So two objects in a category are supposed to be the same. If now, the same. And oftentimes we're just saying the same, but sometimes we also choose an isomorphism. So if we can go backwards, so this is one of the requirements, and going back and forth is now really an identity of the morphism. So if we have some morphism F, so I have some morphism backward G, and G composed with F is identity. Let me call these objects something, X and Y, and F, sorry, I'm ahead of myself, is identity of Y. So this is fine and good as an notion and equivalence inside a one category. And I will show you a problem with this in a second when we go higher up. But before this, let me convince you that the original notion of Eilenberg and MacLean from 45 of what it means to be an isomorphism in a category is actually a different but equivalent one. So instead of requiring this G to be an inverse, what they do is they require G and G prime, and they are acting as a left and a right inverse for F. So for example, you have GF is identity of X, and F composed with G prime now is identity of Y. So the first condition saying G acts as a left inverse for F, and G prime acts as a right inverse of F. So do by chance remember, and I want to, I'm sure that most of you have seen this before, so let me try to ask, why is why are those two notions equivalent actually in a category, in a one category? Just go ahead. There's nothing being too easy around here, so if you would help me out. I'm sure that several of you have seen already why F is invertible. So F and right inverse.
You just check G, F, G prime, right? And you notice that this is equal to G and to G prime.
Yes, that's very good. G, F, G prime. Sorry, I wrote the wrong composition. Yes, so this is once, because we can use the associativity. We FG prime is just the identity, so it's the same as G. But on the other hand, we do GF, and so this is identity of X. And so we can do just G prime. So for example, G is equal to G prime. And this will be useful in a second, like this particular proof, for example. Because in a second, we don't want this equalities anymore. So maybe this would have been a level 1 consideration. In a one category, we have equivalent notions of having a left and a right inverse, and of having both a two-sided inverse. But this already fails if you look at two categories. So if we increase categorical levels, two categories, once again, if I mean something weak, I would say by category. Two categories really a strict one, strict composite. So you have now objects. You have one morphisms, so which are in my pictorial language, something like this. And you have two morphisms in my pictorial language, something like this. Two morphisms. And now you are able to compose those strictly, and the axioms for unitality, associativity, and for interchange hold strictly for those. So let me just put strict axioms. Okay. So what is the natural notion of sameness inside either by category or two category? Have you encountered something so far? So you still can just dismiss the two morphisms and go for isomorphisms. This is perfectly fine. And sometimes this is what you want to do. But instead, sometimes you want a weaker notion of equivalence. So which kind of notion of equivalence would you usually expect? So when is F inside a two category, let me give it a name, maybe inside of C, some two category. When is this guy any notion of equivalence? When we do when do we consider two objects of C to be the same in a sense? Maybe most prominent for C being the two category of all categories. When do we consider two categories to be the same in some sense?
Well, you want a map back and natural isomorphisms to the identity.
Exactly. So now I'm one step up the categorical level. So I want to map BAP. So this is, as Sebastian said, G. But now I look at the compositions GF and FG, and now I have more space for identity to go to identity of X and identity of Y. Namely, I can now require a natural as an isomorphism here. So this is somehow inside a two category inside the two category of categories. Those two cells are required to be isomorphic. So this is now different than just saying it is the identity. We have chosen certain isomorphisms, certain two cells, which are invertible right now, but they are not necessarily identities. And so this this records for you a notion of equivalence in a two category. F is an equivalence. In a two category. But I created a choice around here once again. It was a non-trivial choice having this isomorphism and having this isomorphism. So I can just require for this to be out there, but this choice is not unique and not unique in any possible sense. So here's an example, and I will go for. So consider a two category, and just so that things have names, I have a single object, let's call it A, and I need to have at least one morphism, namely identity of A, but I'm refraining from having any further one morphisms. And instead, I will have a morphism an invertible isomorphism from identity of A to itself. Let me call it something. Once again, let me call it T. T is invertible. So I can now compose this isomorphism with itself an arbitrary amount of time. So this leads to a whole Z of two morphisms, two endomorphisms of identity of A. So by this, I mean, I can also, I have postulated that there's an inverse for this generator T, so maybe generated by T. And I have postulated that there's an inverse. I can just do like this. And now there's a whole choice. I can look at A, and I can look at the arrow identity of A back and forth. That's perfectly a fine choice. But now I can choose different isomorphisms to go from identity of A. So I can take T17 to identity of A, and the other way around, I can say identity of A composed with identity of A. Well, this is now T, I don't know, 23, going the other way around. So those 17 and 23 were completely arbitrarily. I just picked something. And these choices are random in this sense, but I can just choose anything I like. So gives many, and you can vividly imagine that those choices are not equivalent in any sense. So if I choose 1 or identity or 17, none of those is going to be equivalent in any sense. So I have a variety of non-equivalent choices. So right now I have a notion of equivalences, but it's depending on choices, on a variety of choices, which are not coherent in any sense and which are not equivalent in any sense. So instead, we can also consider a notion which is, I think it's a more popular notion, particularly under the name of coherent equivalence in conformal field theory, say, but we can consider the notion of a joint equivalence or coherent. So for me, this will be synonymous today. In any given two category C. So this joint equivalence will be very similar to what I started with before. So I still have an F and a G, and I still want F and G to be isomorphic. But now I have a specific chosen isomorphism. Let's say this is alpha and this is beta, GF. I think this is not compatible with any notation. I'm sorry about this. But now we have some condition about alpha and beta. So far, this is just an equivalence as we have discussed it before, but I could do anything to it. I could choose any alpha and any beta being isomorphisms around there. But right now I have a requirement for this. And this requirement are the triangle identities, as you know them from a usual adjunction identities for alpha and beta. So, for example, I could do something like FGF. I could now go with alpha F to just F, and I could do F beta in order to go back to FGF. And this is a well-defined 2 cell, so I would ask this 2 cell to be just the identity 2 cell of FGF. And indeed, it suffices to require only one of those joint equivalences. Um, 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 uh, because we're in the dimension 2, so one of the triangle identities already implies the other one. This is not true as we go higher up the dimensions. So one of them is now, what about? So everything's strict, n equivalences in n categories. So what about this? How do when do I say are two objects of an n category the same? So far, if you look at this, this was inductive. However, it was hidden behind our usual knowledge, I would say. We defined isomorphisms for one categories. Now we have one categories of morphisms, say from X to itself or from Y to itself. And we can have isomorphisms in this one category. This gives me a notion of equivalence inside a 2 category. I can now continue inductively saying what an equivalence in an what an equivalence in an n category in an by saying, well, in a 3 category now I want those compositions now to be not just isomorphic to identity, but being inside a 2 category, being the same as in equivalent inside the 2 category, which is defined by Y and X. And I can do this inductively. Notion of equivalence. But there are two possible, there are two drawbacks to this. First of all, this is not encoding what we think of as equivalences inside, say, a 3 category of 2 categories. So drawbacks. So first of all, not. As the usual, and depending on your background, maybe you don't have a usual notion of sameness for 3 categories, but let's say usual in the literature, notion of sameness. For n-1 category, so this is a prototypical example of an n category CAD. So this is not the same it deviates starting dimension 2, and something which is also not the same, or at least not so clear to me, at least before, was how can we promote this unique notion, promote the notion of sameness to a coherent one. So far, this was very categorical. There was no homotopy theory in here, but if you know me a little bit, this is what's going to come in to help us at least to decide for the second, but also for the first problem. So let me pause here and ask whether there are any questions so far. Okay. So let me be slightly more precise. So I have so I said something about inductive definition for n categories. So I could just take n categories to be categories once again strictly enriched in n-1 categories. And so this is an induction. I should give you some base of induction. So for n equals 1, this is the usual notion of one category, so categories which you know and love. Then the notion of two categories is just the usual notion of strict two categories. And if you totally want, so you can also go for n equals 0. These are just sets, so categories enriched in sets where you require all the mapping sets, well, to be sets. There's nothing to be said there. So for n equals 0, this is just the same. And you can do a limiting procedure to this. Now for omega categories, you can, so for, if you unravel this for n equals, for some fixed finite n, you will have categories which have cells in any dimension up to n, which compose satisfying strict axioms, as I was saying before, at every level. And now you don't restrict the level of the morphisms. So category like objects. Let me stress once again, strict objects with at any level. And suddenly, so before, notion of equivalence was somewhat unambiguous, I would say. You really want to go back and forth, and more or less you want the composition to be an equivalence of the previous level, the equivalent to identity on the previous level. But now there's suddenly more than one possible things which you might want to require. So there's an inductive notion of equivalence, which is similar to what I have been describing, and it does occur in the literature. It's not very central, I would say, and instead, it's finite at some level. It adds with an identity at some level. So you don't really take advantage of your cells going all the way up. Not well. An equivalence for some n. And instead, the notion of equivalence inside an omega category, which I want to concentrate on, is the so-called co-inductive notion of an equivalence. of an omega equivalence. Let me stress this. So I don't require the tower of witnesses to stop at some certain point by being an identity. I can just go on infinitely. And so I promised you some homotopy theory. So let me maybe state a theorem due to Lafont, Mitailler, Verojkevich. And as I said, homotopy theory, you will see that we are going into some notion of homotopy theory. For me, it's model categories. There's a model category structure. On the category, on the one category, on omega categories due to them, so that, so let me try to characterize this. I told you what an equivalence inside an omega category should be, but this leads also to a notion as you would usually define it, namely being fully faithful and essentially surjective. You just need to make sense out of this. So weak equivalences are weak equivalences, let me say, are based on the notion on co-inductive of omega equivalences. And then let me say something which is characterizing. I can look at the n cell. So in my pictorial language, this was the 0 cell, this is the 1 cell, this is the 2 cell. Now I have a 3 cell. I think this is more or less the borderline from my drawing. So I have DC, and I have a boundary of this n cell, which is everything in the n cell but the top dimension. So for the two-dimensional one, I would have something like this. This is an inclusion, and the set of all of this for any n greater or equal than 0. These are generating cofibrations. So this fully characterizes now a model structure if you believe that there's a characterization of omega equivalences based on this co-inductive notion. So let me point out something which is useful. The fibrant objects in this model structure are everything, so every omega category. And so as you have a model structure, you can consider, and let me do a contour, anything in any omega category, namely, for example, the one going to having just two objects, no morphisms except the identities at all. I can look at this having a single object. This is another omega category, and there's an obvious fold map, which is an omega functor, which, as you can imagine, this is compatible with all the compositions which you can imagine behind there. So as you are in an omega category, you know that you can you will be able to factor this into some fibration. So let me call this P1 into some weak equivalences, which is at the same time a fibration and some cofibration. So fine, this P1 exists. And it is a bit mysterious, as I said it right now, but instead, let me go back to the very beginning. Our theorem is saying we're now, so this P1 is a model, sorry, this is maybe not our theorem, this is due to set of 5 to 6 people, Ara, Buroni, I think Mimram, Metayer, and Malbos, I think. So they show that this P1, which I just defined, is characterizing coherent omega equivalences. And instead, what our theorem is about making this P1 more explicit. So as I said, there exists something which fits in this triangle, but instead our theorem says we can make this more explicit. So first of all, we give an explicit construction, but this is maybe not, this is a subject for another talk. Something which I can say quickly is that our construction is finite in every level, finite type, let's say. So you cannot expect this construction to be finite in any reasonable sense, but instead you only add finitely many generators at a given level. This is what I mean by finite type. And this is a glimpse of our theorem. But we have a more explicit construction of this P1 so that you can completely determine it to any finite level. And I think something which we, we discussed at the very beginning, what an equivalence in one or two categories should be a coherent one. And we recover these precise notion out of our notion for infinity. So I think I'm roughly at my time, right? So thank you here.
Okay, thank you very much for the talk. We're actually technically a bit over time, but still inside question time. So are there any questions before we stop the recording or comments? There doesn't seem to be any questions, which means that the talk was perfectly clear. So let's thank our speaker again. And okay, I think we can stop the recording now, but of course, everybody is welcome to stay if you have any more off the record or offline questions. But let's see if anyone can stop the recording, please.
I did stop my recording.